All right, hi everyone. Thanks for coming to the September edition of the Fission Reactor call. I'm calling from a beautiful chateau in France. Today we're going to talk a little bit about things Quinn has been up to with spec writing and the evaluation model. And then I also have some mixed bag news regarding encryption and just general size. So I guess I'll let Quinn start. Quinn, take it away.
Yeah. So last time we spoke, I showed off a lot of the work that I was doing with kind of like differential data flow inspired approaches to data log. All of that went extremely promisingly. I showed off some demos of the implementation I made of VMware System DVSP that allows you to do differential computation over streams, and the way I was compiling data log to that. That experiment, I think, was a success. So we've kind of moved on to the spec writing phase of Dialog now. And that's where I've been spending my time, just getting a lot of the details down on paper in terms of how you implement these circuits and compile to them from Datalog and so on. It's been a slower month because of some non-work related obstacles that have come up, but hoping to continue that after our work retreat in a week. And that's making steady progress otherwise.
Awesome. I'll give the quick update on encryption research. So the short story is we spent a bunch of time over the past couple of weeks, months, thinking about, well, okay, what are the expected user behaviors for encryption? And if you have a certain fact, what should that also give you access to? How do we keep it from having to be manually defined every time so that we can do this, at read time, all these things. That actually works pretty well. The problem is if we encode them as their own item in a flat space, just the names, if we want to have these, give them encrypted names with cryptographic proofs, just the names are often bigger than the facts, which is not great, right? When you have 256 byte names, and then you need to, maybe sometimes having up to 256 byte witness on that gets to be a lot. So I have been rethinking a little bit, okay, well, how many things can we stick together? How much information does that reveal? Is there a thinner thing that we could use that's different from how we do things in the file system, where we can often justify 256 bytes, not bits, bytes, against a file that's 3 megs, right, or something, right? When these are, let's call it 100 bytes, it's now the name is so much bigger. So that's kind of where we're at with that. The really high level on the actual system is every row has its own key. You can, and it has a hierarchical encryption based on entity, attribute, then value in that order. So if you have access to the entity, you have access to the whole thing. And then for things that have causal dependencies, if you have something later in the dependency chain, you get the earlier items, because that's going to be a requirement for something like RGA, where we go back.
I'm a bit surprised that the facts are so small, given that they probably will often encode the names, unless, of course, the names are indexed, which is definitely something I was planning to do in my database implementations.
So maybe I should explain what I meant by name. So it's not the name of something like, this is at a different layer. This is at we have an encrypted blob, random looking bits, and we need to give it a deterministic label so that you can uniquely identify that specific one.
Yep.
And be able to search for them, including for ones that you don't know that exist yet, right? Because it's not a stream, it's just we destroyed the entire relationship.
Like a
right?
CID, so I expect you're working with CIDs, basically.
At a different layer. This is a pointer machine. With CIDs, you would need, you won't know what the CID is until the fact exists. So if I've given you version, in a stream, 1, 2, 3, you won't know what 4 is called.
Correct.
right?
Correct.
So we go up a layer and say, this is a pointer machine. If you know what version 3 is called, you'll know what version 4 is called. And you'll be able to construct that. Which is how we do things in the temporal crypt tree on the file system.
Okay.
Yeah. So there are CIDs underneath that to produce the actual Merkle tree. But we have a pointer machine built out of a Merkle tree at the semantic layer above.
Okay, so you have these names, which are pointers to the Merkle tree. And what I'm saying is, aren't the facts themselves referring to those names in the Merkle tree? And how are they so small if they refer to those names in the pointer tree, unless you're giving, say, the timestamp or the sequential order as another key and using that in fact construction?
300 bytes, so like 2,000 bits.
Yes.
It's like
it's
4
costly.
times bigger. It's 4 times bigger than a hash.
I'm not contesting that your handle is huge. What I'm saying is, how is the fact itself so small? Because doesn't the fact contain handle references?
Oh, I see. So there's 2 answers to that. One is they can refer directly to a CID.
Okay.
And we can always hash data to be smaller. We need these larger handles specifically for doing cryptographic proofs that you're allowed to do the write without revealing the name.
Got it. Okay, that answers my question. Now, since you're thinking sequence, can't you have a kind of mix of, hash plus a bunch of contiguous events with a simply order byte, and thus reduce the like sometimes you need to have a cryptography for each thing, but sometimes you have contiguous events, like we're speaking about text editing. Contiguity often happens, and in which case can't you reduce by doing crypto plus sequence when possible?
Yeah, so that is a valid point in the design space, but it does reveal a lot more information about how their data is related to each other.
Fair.
Brooke, did we lose you?
You lost me.
Okay.
To me, I was like, did everybody just leave? No. So there's a valid point in the design space, but now we're starting to reveal how everything is related. And so you can start to say like, okay, I know that there was a bunch of updates. This is the file I'm looking for right here, because it's, most of the updates in a sequence are here, and there's 2,000 of them, and there's none others over here, right? So I've thought a little bit about like, do we chunk them? Do we do chunking and then randomization, right? Some of these strategies. Do we use a lighter weight witness, right? So there's some questions about like how much does it matter?
Yeah.
Right. So it's in that kind of a balance right now. Like we know how to do these things, but they're kind of heavy.
Because if you chunk them, you can actually take these 20 contiguous things and make it look like a single one. But and then nobody will know that they were 20. Yes.
Yeah.
But you have you could have a sequence when you decompress it.
But you might not be able to decompress the whole thing. You might only have access from a certain slice, right?
I'm assuming that the chunks are across access boundaries.
So a design goal is to have very flexible access so that at share time, you can decide what somebody has access to.
Makes sense.
So obviously, all of these things together don't fit. So something's going to have to give, right?
Yes.
And so, like one version of this idea is if you imagine an RGA, right? So you have one line and then another line sticking off of it. You do this, okay, I've got a fork operation with different writes to it. And maybe that's something that users would be comfortable with, to say like, this is a new author or something, right? And then do them that way. And then we can start chunking them up in a different style. Something we've thought about, it's not as flexible. Don't totally love it, but might be required. Sorry, the other thing I didn't mention earlier in the call is we actually now have some early parts of these things written up in the repo. So not like in huge detail. Quinn's been out a little bit. I've been traveling around, sitting here, but there's actual text that is legible now on Fission codes, GitHub Fission codes /spec in a PR. So it's coming along.
Yeah, it's a very work in progress, but I've got semantics for kind of the intermediate data log representation of some of this stuff, along with a lot of the early details on what the differential circuits look like and what sorts of operators they can support. There's still quite a lot to fill out, but starting about 2 weeks from now, when we get back from our work retreat, that's going to be my focus full time. Yeah, it should be that one, Sodium.
Yeah, and I think we're probably going to end up getting a lot done in person, whether or not that ends up being fingers at keyboard, but like at least talking through things of like, how will we use this? What are the interfaces? All of those things, which tends to happen when you get, well, these kinds of nerds together. So also, just while I'm looking at the grid here, Zishan also just joined the team and will be very likely contributing to the database work. Zishan, do you want to say hi and maybe a few words about yourself?
Yeah, hello everybody. Yes, I joined Fission last week amongst things around strange open papers we love. I've worked at Basho many years ago, distributed systems. I worked on a lot of network packet processing stuff at Comcast. I also study programming languages and programming language theory at CMU as a PhD student with Frank Fenning. Excited to kind of hop on board looking at stuff around compute databases and a bunch of other stuff. Obviously catching up on a lot of years of IPFS because I didn't really look at it too much other than when I was at the Basho days during a very different time around databases, very different era. Trying to piece all that together and contribute as best possible.
Awesome, thanks. Great. Before I just open it up in general, Quinn, do you have any other updates, or should we just open up to questions?
While we've been in this call, I've had a couple of DMs from some people asking if they could see some of the differential data flow stuff demoed. I did that last time, so it might be a repeat for some of you, but I'm more than happy to go through that again if we want to spend a couple minutes on that. Sure. Yeah, I'm just setting up my browser now. This is going to be a fairly rough demo since I haven't prepared for this, but I can walk through some of it. All right. Is my screen going through?
Screen showing up, yeah. And I should also, put an asterisk on this. This isn't the final API or anything. We're essentially working with AST here. Yeah,
definitely. So I've been doing a lot of my prototyping in Elixir too. The end goal for all of this is going to be to have this implemented in Rust so that we can compile down to WebAssembly and run in a number of different environments. I've been using Elixir for prototyping. It has really powerful metaprogramming capabilities and so on. And I also do a lot of my prototyping inside Livebook here, which is sort of like a Jupyter style notebook. And again, the DSL that you're going to see here is really just for my own experimentation. It's not what we expect to expose to people when we start shipping like JavaScript APIs, for example. But just to show off a really simple use case, here I have an implementation of transitive closure. So I have some graph encoded as edges between nodes, and it computes all of the paths between all of the vertices in that graph. I do that just using a simple recursive rule that has a base case that copies edges into the path relation. And similarly, it recursively walks across paths and edges to start inductively accumulating all of those paths. And then we wire that up with a hard-coded list of edges and also attach some sinks here. Sinks are essentially operators that respond to information that's being computed by one of these dialog views. and do something with them with respect to the outside world. So that might mean storing them in some persistence layer or making requests or passing them to a front end. And in this case, it just involves passing them to ETS tables, which are sort of like a lightweight in-memory persistence layer that you can use within Erlang and Elixir. So the way I am actually compiling this program to be run is using a technique that I've lifted from some research VMware has done that they're calling DBSP, Database Stream Processor. And this is some work that they further built off of differential data flow, which is a system from about 2011 that was designed for doing differential computation over streams of data, with the idea being to basically automatically take streaming computations and convert them to a differential form that's able to operate over deltas to really efficiently compute changes over some view in response to deltas without rematerializing everything from scratch each time. So yeah, so essentially this DBSP system is a data flow graph that I compile the data log program down to, and then that gives us incremental view maintenance for free. This is an approach that I was eventually drawn to after doing a lot of experimentation with techniques like Dread, which we've talked about in previous sessions, but that underperformed for a lot of real world use cases, and especially for things like the RGA CRDT that we've spoken so much about. So in this case, when I evaluate this program, it's going to output all of the computed edges inside these tables here. These are these in-memory ETS tables that I've talked about that I just have some shims set up to render them into the notebook. But similarly, it's also going to compile that program into this circuit, which I have things set up to visualize here. And basically what's happening here is we compute a circuit representing all of the joins and predictions and so on from the data log view that we defined. And then there's actually a calculus defined over those circuits that allows you to differentiate and integrate over them so that you can compute these incremental circuits that efficiently compute over deltas that get input to those circuits. So that's what you see happening here. We have this generator node that's feeding in the edges that we start with into this sub-circuit that represents one of the stratums in the data log program. And then this basically just keeps recursively calling itself using deltas that end up being evaluated at each step of that recursive computation and doing incremental joins over them and so on. And basically you end up with all of these smaller sub-circuits that compute their own fixed points. And the circuit that you end up with is operating over these deltas instead of the full view, so that it's just doing tiny updates each step. And you're able to walk forward and backward across that timeline. So the system is basically doing that translation automatically. Excuse me. And yeah, just enabling that sort of incremental view maintenance without requiring that the user manually write these performant incremental views. So that last example was just using our hard-coded set of data. But down here, I have the exact same program, but simulating the progression of time by introducing new edges into the system each timestamp. And when we run that this time, we can actually see the way the view is changing as time progresses in response to these new edges being added. Them being added, them being deleted as we remove edges, and the way that flows through to any of the other edges that depend on what has been deleted. So yeah, I'm not going to walk through all of these, but I have a couple other examples that show the way we can compile these data log views into this form. And where things get really exciting is with RGA. As I know PVH in the call knows, Martin Kleppmann once wrote a research paper on RGA. And in putting that paper together, he recorded all his keystrokes to create a benchmark data set for RGA that includes all the insertions and deletions and so on. There's about 260,000 events in it. And It's a benchmark that data log implementations traditionally perform very poorly on in an incremental setting. A lot of the tests that I've done with generally performance-focused implementations take upwards of a minute to run through the entire data set. But using DBSP, the system that this compiler is based on, I implemented RGA in terms of these data flow constructs and was able to run through the entire data set in 400 milliseconds if you do it all in one batch, or in about 800 milliseconds if you do it in batches of 10,000. So that is well within the range that I think is required to give the sort of real-time experience that we would want for a real-time collaborative text editor. And this differential approach is really the first technique that I've found that has been able to give that sort of performance for these sorts of problems, which is kind of why I'm so excited about this technique and why we switched over to spec writing once we showed that it was workable. There's still definitely work involved in getting the whole system built end to end, and especially in Rust, talking to IPFS and working in a browser and figuring out some of these encryption details and so on. But the query engine itself is something that's really started to take shape. And I haven't shown off all the features here, but this version supports most of the things that you would expect from a data log engine for any sort of views you'd want to build for like a front-end local first application, aggregation, negation, joins, filtering, projection, etc. Along with some really promising results in terms of the way we have been thinking about time and wanting to track different snapshots of data as events are added so that you can get really nice like provenance information about how the system changes as new events are added. So yeah, again, a lot of work still needs to be done, but this prototype has been pretty exciting, and I'm really looking forward to working with the rest of the team to build something more production ready. I do have an implementation of RGA down here, which is a little bit terrifying, but this is the sort of thing that happens behind the scenes by the compiler and is really sort of the magic of the approach. It's all just really simple formalizations on top of relational algebra that allow you to generate something like this from joins, projections, and selection.
Yeah, it's also, at least for me and Quinn, very exciting that we have this data log substrate, because somebody could take this and write any arbitrary CRDT in this, and in theory, get similar performance, obviously based on however they write that CRDT, right? But all of the optimizations that we put into this, and as we optimize it over time, will then translate to, like, if we make the engine faster, anything you put on top of it's faster, right? So it makes this really nice general system. Just because Quinn mentioned IPFS and encryption, we're really thinking about these as being completely separate layers. So you will ask for stuff from IPFS, pull it down, decrypt it, dump that into your local store, and then the local store can operate on it this way. So there's no hard binding between IPFS and where we're going to get out of in the store in dialogue, to the point that we're even talking about, like, well, how far can we truncate or shorten the links, the CIDs, because we don't need the full thing probably, right? We probably don't need a 256-bit address space, right? And we can definitely lop off the QM or the Bathy from the front at minimum, right? So, like, do we make it 128 bits? How far can we compress that? Do we have a table, or do we just keep internal pointers? Like, there's some of these discussions as well, just for sheer performance and size locally. I was chatting with Martin a couple days ago about auto merges compression strategy, for example, where which PVH, who's on the call, is involved with too, have gotten it like was it a 10x better than what you had previously, something like that? With the run length encoding? 300x, okay, yeah. So we might be able to use some of those optimizations as well. It's just then we have to hash a bunch of stuff on the other end, right? So, or use these internal pointers.
Is one who's actually implementing a lot of this stuff right now.
Okay. But yeah, which is really exciting. We think we might be able to reuse some of that. So related work, actually technically Reactor work as well. We're replacing or very likely to replace BitSwap with a homegrown protocol called Car Mirror, part of Carpool, which is a broader approach, because BitSwap has this problem where you go back and forth over the wire a bazillion times to get any information. And if we want to get a particular diff, we can just say, hey, select these things for me. It'll grab that and pull those down. And like sometimes you'll have to go back out, but we can do that in a much faster way. So we're definitely thinking about like, well, how much is going over the wire? What's the latency? What are our round trips looking like? That should also then benefit this work as well. So yeah, and actually when I was at Strange Loop and I mentioned that, I had a few people in the Web3 space come up to me afterwards and be like, that would be really nice. When can we see it? So we have a Go implementation of it coming in the next wrapping up now. So let's call it in a couple of weeks. And then we can write a version for the browser and then move over to a REST implementation as well. So yeah, lots of stuff going on.
Something I didn't touch on too much, but Brooke mentioned that this separation between the query engine and IPFS means that the persistence layer doesn't need to be baked into the query engine because all of that translation happens at these source and sync nodes. But there's actually nothing that imposes like the requirement that those need to be nodes that have to do with like persistence or reading or writing data. And it also enables the sorts of functionality that systems like Daedalus and Bloom were going for by having like source nodes at the ingress of the data log query that handle like message passing or sending packets or triggering callbacks inside user code. And we have some interesting ideas on how you might be able to use that sort of thing to get really tight integrations with, for example, front-end JavaScript frameworks. So you can track provenance between the data log view that you are computing and the like event handlers and the UI that are causing data to be consumed or produced for that data log view. I don't have much to show off there because it's mostly just been a lot of experiments to prove that the idea works rather than actually trying to integrate it into anything. But I'm really excited by some of the possibilities that it might open up for some of the use cases we have in mind. Oh, and I do want to, Sodium sent a link to differential data log, which was the predecessor to DBSP. Differential data log is from a few years ago, and that's a Haskell compiler that compiles down to differential data flow. But there's a few limitations in that approach and a couple of complexities with differential data flow that they were working around that had problems in terms of both compilation speed and the complexity of the runtime itself. So DBSP tries to really constrain the system to exactly what they need for compiling relational algebra down to those circuits. So it's an improvement over what they have previously been doing with differential data log for that use case.
Marc-Antoine, you had your hand up a second ago.
Yeah, I was just curious, how much does this, like you see you're rewriting in Rust, how much can this reuse the differential data flow library, which is already there and in Rust, or is that something you're recreating also?
Yeah, it's a good question. And Zishan actually asked it when I was first walking him through the system too, since he has some experience with differential data flow from previous roles. And that's still something that I think we need to talk about a little bit. One of the really, so DBSP is actually partly implemented in terms of differential data flow. It doesn't have a hard dependency on it. They vendored the pieces of the system that they care about, which for the most part ends up being their definitions of lattices, semi-lattices, and the data structures that they use for storing deltas and traces of deltas. So there's the possibility of possibly wanting to reuse some of that simply because of how performance focused they have been in building those data structures. But there is also some questions that need to be answered around compilation to WebAssembly, because WebAssembly does impose some constraints on the sorts of Rust that you can write. That's
thanks.
not my expertise. We have people at Fission who know a ton about WebAssembly, Rust, and the interplay between them, but we haven't sat down to kind of walk through the system with them and see what pieces of it are conducive to reuse there.
Yeah, just to add, like, yeah, having done differential time in the past, like I think there on one of the GitHub issues, I think somebody brought up like a way to compile it out to WASM. I think Frank McSherry and co were like, no, I don't know about that. They have a company obviously trying to build on those things with Materialize. But yeah, it's an interesting question. And that's one I had to Quinn as well, right? Because there is a lot of work and there's a whole lot of papers on the stuff around shared arrangements, which is some really interesting optimization they do around memory. Do those things really matter when you start moving toward the WASM plane at all either? It's kind of an interesting kind of question about implementation and use that we have to answer at some point.
So interestingly, DBSP doesn't actually make use of shared arrangements.
Right. Exactly. Right. Yeah. So that's
differential data log did, and that was one of the big sources of compilation slowdown. Shared arrangements were basically a way of sharing indices in a stream setting. You would look at the data log view, see what indices were required for different joins, and then see where those same indices might show up in multiple places in the program. And then extract that out into like a shared subrule that all of those rules could pull from. And that was a lot of work to kind of solve for the optimal shared arrangements. And then also introduces, if I recall correctly, it also introduces some thread contention if you're trying to have multiple readers and writers to those arrangements, versus if you just have the data flow circuit with all the producers streaming directly to their downstream consumers. Sorry, did I cut you off, Zishan?
No, that was a good run through of the work.
I find myself thinking again about the problem at the beginning. Sorry to, I don't know if we are done with this one, but the problem of having these Merkle trees of changes. And I keep thinking one encryption per stream, and if you want to share with someone else a subset of the stream, just re-encrypt with the new permission. I know it's something we've discussed before, and there was a reason you weren't that happy with it, but trying to see what's the...
Because you have to be online. So that has a liveness constraint, and we have a offline first constraint, right? To do the re-encryption when somebody wants to access it, so, right?
Is that so? Let me think about this. Probably true. I wonder if you could delegate that to a proxy.
But then the proxy has to be able to decrypt the data.
Yes. The question is, can you delegate re-encryption? And the idea is, if you have anybody you've trusted with the original stream, they have the decryption key. So you've distributed the decryption capability.
Yeah, precisely. So I've delegated to you some subsets. You could encode that in your own store and then share another stream, but then the person you're sharing to won't get updates to mine unless it goes through you.
Correct.
Right?
Well, I mean, well, unless you come back online.
Unless I come back, unless I
And
come
then
back
there's no
online and then
problem.
you come back online, right?
No,
there's
but
this multi-way sharing.
it has to be
challenge.
multi-way. I agree with you. If they always access you through me, there's a problem. But if I'm a temporary holder of the stream copy, like they make a request, you're not online. I notice that this is that I have. So I say, okay, well, here's what I can get you. And maybe it's not even the full thing. And then you come online, you become aware of the request and you add stuff to it. And maybe I keep decrypting it because I'm aware of the query. Even if they're not online, you go offline, they come online, they can read it from me. So there's a way to make it distributed. I don't know if that's viable for use case, but
yeah. So I mean, look, it's worth thinking about, right? I think the system doesn't fall apart under these pressures, right? We can essentially say that this is like a lot of latency or something, right? Between the different parts. They'll continue to work. This is a speed of delivery question, I guess, right? Yeah.
No, there's definitely something there, I think. Anyway, this is a conversation maybe we should take offline. You have another important one here on vector clocks. I don't want to distract.
So the comment in there, we're having a side discussion about a sync protocol, which I can also take offline. It's like slightly tangential. Well,
it's interesting.
Okay, fine. I'll go into it a little bit. So my understanding, which could be completely wrong, Peter and Alex, right? It's possible it's completely wrong, is that in auto merge, this sync protocol essentially collects up the revision history, essentially like a vector clock, as a Bloom filter. And then you can use that to match on, am I ahead or behind by matching on the filter with some false positive rate. And then maybe like with a hash as well to be like, well, you know, there are adjustments on Bloom filters, right? That you can get a little bit more accuracy on. And then that gives you a sense of like, are you ahead or behind? Is that roughly correct?
So the sync protocol assumes you have an iterated collaboration and has a bunch of optimizations for when you resync with the same person. So what you do is you start by sending your heads. If you can determine from that what you need, then you just request it, it's sent over. Actually, sorry, more accurately, what you do is you send someone your heads and then they look at that and say, do I know what you need? Okay, I'll send you everything I know you don't have. And then the Bloom filter is used to create shared context from between your last known shared heads to your current heads. So that way you can walk through the Bloom filter back from, you know, what your heads are until you find something that they have that's in their Bloom filter. And then you go, okay, well, if they have this commit, I have everything before, so I can stop looking. And so then you send that, and then it's a fast path there if you know. Of course, you might be wrong, might be a false positive in the Bloom filter. That happens 1% of the time, in which case they reply and they're like, I don't know how to apply this change. Could we try again? Then you send them that one change, which 99% of the time with the current tuning is enough. And then there's a 1% chance they're like, actually, funny story, I need the one before as well. But you know, this becomes then actually. So usually you have a single round trip 1% of the time. You do 2. That's it. Does that answer it? It's honestly, I found it kind of difficult to wrap my head around when I was first like documenting it. There's a bunch of sort of unintuitive, like you don't send what you have, you send offers more than requests. And then people reply with what they need. And no, wait, got this backwards. It's been a little while since I had to work on it. But it's all documented in that link that I sent back when I wrote the documentation back when I did understand Chrome. So if you have questions after that.
Awesome. Yeah, I'll give it a read again. I think I read it a while back. How this differs from car mirror. So it's not necessarily even for this specific body of work that we've been talking about on this call. It's solving a general pain that we have with IPFS. Down in libp2p, you have a lot of round trips. So if you have a very wide tree and you get the top element, you will see all of the links on that's very wide, and you'll be able to ask for them all at once. If you have a very deep tree, you have no way of knowing what those exact hashes are. So what we do is we build up a picture of what the remote has by going through multiple rounds of, hey, I want this thing, and here's a bloom filter of what's already in my store. Don't send me these things. That is a conservative approach. So it'll sometimes false positive match, and it won't send you something that you do need. So at the end of each round, the responder says, hey, I'm missing these. Could you send me those ones again? But it knows not to send the last bloom filter, right? And now you can go like, well, I know that I know those ones. Let me, resize my bloom and, all of these things, and maybe add some other stuff to it, right? Because I've gotten things in the meantime, right? And then you go through this process a few times, and it just cuts down on the number of round trips you have to do. It's just a very simple sync protocol where we don't do anything like too wild. Like there's a whole subfield of research in this area, right? So it's like a simple optimization we can apply to libp2p, basically. libp2p has these two problems. One is the latency, and the other is because of the latency, sometimes the connection manager drops in the middle. We can implement this sync protocol over just boring old HTTP and not need to deal with libp2p for a lot of cases. And then also implemented in other, Duo WebSocket version, which is then libp2p-able, and all these other things too. But we just wanted to work in the browser to get started and do this multi-round but cut down protocol. Further work after that is, so that's a point-to-point protocol. One really nice thing in IPFS is you can get data from multiple sources, kind of like BitTorrent. So there's two layers, a trusted layer and then an untrusted version where you can go out to a DHT. Without a DHT, we know that most people get data from a small number of providers that have large data sets. And that might be caching from a previous request from, even though it got uploaded over here, they've seen it before and they've cached it, et cetera. So you can get it from multiple sources. So the next step up is having the providers coordinate, or at least say, hey, I think these providers have it. You should also ask them for the next fragments of the data. So we haven't written the spec for that yet. There's a bunch of work and thinking to go into that, but that's essentially to recover this multi-stream version. And then the last one is a completely untrusted version where you're essentially announcing to the network, hey, here's all the blocks I have. That's super scary because now you're essentially doxing yourself, right? Like, hey, not only am I asking for this CID, I'm asking, I also already have all of these things. By the way, I'm a political dissident or something, right? Like it's kind of bad. So Quinn and I have riffed a little bit on, using oblivious transfer protocols and all these things. We're not cryptographers. So at that point, we would probably partner with some of the cryptographers over at Protocol Labs who have like research cryptographers about the appropriate approach and what the trade-off in performance is and all these things for that. As a really simple step in the middle there, we've been talking about running a group called the Content Addressed Alliance. So this is more on the community side of things, where we could just pre-share and pre-fetch data between each other, and then make sure that there's lots of seeded data that then something like this multi-provider trusted protocol would be able to provide better without having to go all the way out to a DHT. So it should, along a few axes, speed things up a little bit. So that was a long rant about a sync protocol.
I remember hearing about IPLD, and it was in flux at the time, so I didn't dig into it as much as I wanted, but I did they were talking about doing this in IPLD and having basically sending the whole query, including recursion, so that you were speaking about the tree depth as opposed to tree width. And I remember it was possible to send a query spec, so you could say, this is what I want, and everybody look for it, kind of.
Yeah, so that's GraphSync, which today is a point-to-point protocol, and is only implemented so that you can grab the entire thing. You can't do it incrementally. But I mean, I guess you could send in multiple phases. And again, it's only point-to-point today. The main problem people have with it is that the query language is non-intuitive and very complex.
Yep, I remember.
Yeah, which is the main complaint. So something that, again, we've kind of kicked around as an idea since we're doing all this data log work. And in fact, it was either Philip or Quinn who originally came up with the idea. I can't remember who, between the two of them. But like, what if we had just a really simple data log plus negation, and we used that as a substrate, like as the intermediate language for doing these remote queries? Because data log describes graphs really well, and sections of graphs, and skipping portions and all of these things can be very rich. We could write a very compressed version of the IR that is good for over the wire, and then you can write a nice high level language that compiles down into this medium range, and now we have a common language that we can describe literally anything in a graph, right? Will that be faster or slower than GraphSync? Don't know, but we're doing all this work to do incremental view maintenance, right? So then we could maybe reuse some of these tools. So it's again, something we've kicked around internally. When I mentioned it to people, because there's a few people inside of PL that are looking for like alternatives to GraphSync. The reaction is basically like, so you're going to get rid of GraphSync and introduce another thing that I don't know anything about, right? So we'll see if that goes forward. I think it's an interesting, promising idea. That we would maybe do like a proof of concept of, and just sort of like see how people feel about it and then go from there.
The way I was thinking about it was almost like a GraphQL, but with data log as the query language. Since GraphQL doesn't allow you to represent like arbitrary recursion, you can say like, I would like to traverse 3 levels deep, for example, but you can't represent.
No, GraphQL is so misnamed.
Yeah, but data log allows you to represent all of those other like graph traversal ideas that you care about in situations like this. And
yeah,
I think it could be.
But GraphSync does allow recursion, right? So I absolutely love the idea of compiling your data log queries to GraphSync. I don't know if it's easy or hard, but certainly an interesting problem.
Yeah. Well, the other nice thing that doing raw data log would give us is we could just apply it directly onto the block store, which we're going to be doing anyway.
So skip the GraphSync layer and build a new GraphSync layer based on data log and
basically, right?
But and it's still a good idea because you can still leverage the libp2p layer to distribute the logic.
Yeah,
that sounds good.
The other nice thing about this approach is you can compile lots of different high-level languages down into data log. So you could hand people who don't need recursion GraphQL, and we could compile it down to data log. Right. So it's like it opens up all these, or SQL, or some unique special, existing IPLD selectors could also compile down to it, right? So it's like it ends up being this really nice common language that we can then apply in a lot of different places.
One of the things you get with the incremental view maintenance aspect of it too is, in theory, the ability to deploy like an IPFS gateway that sits there running a query as almost like a subscription that it can feed like emerging results to subscribed clients, like you get with GraphQL subscriptions, for example.
Well, I do think if you've got that written, what I was saying about sharing queries and sharing rewritten streams does become almost trivial. I'd really like to spend time exploring that deeper with you. I think it's still what I see as the simplest approach. encrypt at the stream level and re-encrypt, because you don't, when you define a subset for someone, I think you're very likely to reuse that subset for a lot of people. You don't need to define subsets of your data that often. That's an intuition that may be wrong, but I think that's pretty much true. I mean, of course, you have this, oh, I want to share this one thing, which happens pretty often, but still, my claim is you don't define that many subsets that aren't reused. And then let's actually reuse it rather than thinking about how can I arbitrarily slice and dice what I've published one way after the fact, which I think is a harder problem, but I think it might be easy. The re-encrypting subsets, I think, is more. And it's a very, it's very compatible with the OCAP logic that you're using otherwise. I'm giving you access to the subset handle.
Yeah, which today in the file system, we do entirely with encryption keys. And we do have this really granular encryption, right? But then again, we're working on much larger data, right? It's like entire files, not just little single tuples, right? So.
Yeah, but my point is that each data log claim has an originator and hence a stream from that originator in the first place. So that is one line of encryption. And then there's what you're sharing. That's another line of encryption. Anyway, I don't want to push too hard on this, but I really want to see what you see as the problem with this approach. If
the streams, basically, right? So we can take it offline. We've had this conversation.
Yeah. Let's. Sorry.
Awesome. So just a quick time check. We have 4 minutes left. And somehow I was worried that we weren't going to fill the hour. Any final burning questions people have before we wrap up? All right.
How long do you think the road to React App is?
With the database in particular. So we have to actually write that thing first. Once that's written, once the WebAssembly is written, it'll go immediately over into integration into the Web Native SDK, and we will write demo apps with it immediately, basically. So the hope is that we can provide people to start a very simple builder syntax, and then also hand them like it's essentially something pretty close to, but like JavaScript native data log, and then maybe even SQL, because we can compile all these down. But just to get like up and running at all, after the WASM ships like weeks. How long is it going to take us to write the rest? Sort of an open question. Quinn, I'm not going to hold you to any like specific numbers, also because we're going to hand it off to other people, right? How long do you think it would take somebody roughly based on your proof of concepts?
So with the proof of concept, every iteration I basically started from scratch, and the differential version of the prototype was about 2 weeks of work, but it's definitely research code, and there's pieces of it that I know are wrong or like not as performant as they should be. I think it could be possible for someone to have an MVP running with feature parity to the prototype in like a month, but that's ignoring the integration with any of the external systems like IPFS purely since I don't have as much experience with those code bases or those protocols. And one other caveat I want to add to Brooklyn's comment about weeks to React app is that, correct me if I'm wrong, but I believe you were talking about kind of calling dialogue directly with the builder syntax and not through like a more tight integration with React. I have ideas about what an integration like that might look like, but we have done very little work in terms of actually trying to hook into React or extend any of these front-end frameworks to work with data log or anything like that. It's just mostly a lot of like conceptual ideas.
That's helpful contextualization.
Mm-hmm. The prototype I have here is actually, the code is surprisingly small. I think the entire prototype, DSL, compiler, visualizations, like circuit construction APIs, everything ends up being about 4,000 lines total, I want to say. Which obviously that's going to be larger in Rust because Elixir is a fairly terse language, but there's not nearly as much code here as you might expect for how much it's actually doing. Most of the heavy lifting happens in the formalization itself.
And I understand that that's going to be what Zishan's being hired to do, or contribute to at least.
Among other things, yes.
Yeah, yeah, definitely can help out on the Rust side. Obviously, have a lot of background. Some of that.
Part of the reason that we're writing a spec for it is that we have like Rust WASM specialists on the team who should then be able to take a spec and implement it, but they're still probably going to have questions about like, hey, what does this term mean? How does it actually work? It looks different in Rust than it does in Elixir. What's the right approach, right? Like these kinds of things. Then I assume that'll be where that'll be helpful. So.
One of the things that I imagine we'll be fleshing out over the next 2 or 3 weeks, especially, is some of the like implicit knowledge gaps between me building this prototype after spending like literally months reading data lab papers and passing it off to other members of the team who have a lot of Rust experience but haven't spent as much time with like data lab semantics. And so there's probably a lot of background information that we're not necessarily aware of that we're going to need to figure out how to capture in the documentation and specifications.
Well, I'll be happy to proofread the specs at least.
I'm very excited to pass them off to you. There is a link to the pull request, but it's very work in progress.
I saw, yes, but I'll keep abreast. Amazing.
All right. Well,
okay.
thanks everyone. I'm at least going to turn the recording off now. So see you all next month.
Thanks for joining.